In this video, I'm going to go through the concept of density, show you how to do some density problems, and then show you how this density can kind of be used here in the real world. So, density is just this relationship here of mass to volume. A lot of times when I ask this question in class, I would say, which is heavier, a pound of feathers or a pound of lead? All right, we know that a pound and a pound are the same mass, but sometimes when I put people on the spot, and give them this question and make them rush, they would say lead because they're confusing the idea here of density and mass. All right. Lead is definitely way more dense than um, feathers. All right. Think about density as being like how much stuff is packed in a given area. A piece of lead has way more stuff packed in a given area than feathers would in the same amount of space. All right. So people that say that, lead has more mass, even though they're both a pound, are confusing this idea of density here. But density is just this relationship of mass to volume. The equation to figure out density is going to be mass divided by volume. So D equals M over V. You definitely need to know the equation here because you have a derived unit here, essentially, mass divided by volume. The units aren't going to cancel. So your units for density are typically going to be something like grams per milliliter or grams per centimeter cubed. The mass and the volume units do not cancel. Density is what's considered to be an intensive property. Basically, the amount of the substance does not affect the density. So if I brought in a big block of gold and I brought in a little flake of gold, because they're both gold, they would have the exact same density of gold, which is about 19.3 grams per milliliter. Uh, it doesn't matter how much of the gold I have because density is an intensive property. As long as both substances are gold, they would have the same density. So don't be fooled by that. You do need to know how to use the density equals mass divided by volume equation to solve for mass or volume as well. So those two equations are listed here. So if you wanted to solve for mass, you just rearrange the equation. It'd be density times volume. And if you wanted to solve for volume, when you rearrange the equation, it would be mass divided by density. So you do need to know all three of the equations here. Sometimes it makes it helpful to use something called the DMV triangle here. I show you this just because it's a way to help you remember the equations. So what you do here is you draw a triangle and you do DMV. And basically any letter that's next to each other would be multiplied and any letter that's kind of on top of each other would be divided. So for example, if you wanted to solve for density, if you were looking to solve for D, you would have mass over volume. So mass divided by volume. If you wanted to solve for mass, though, well, look what happens. Density and volume are next to each other, so it's density times volume. And if you wanted to solve for volume, all right, it's mass on top of density, so mass divided by density. So that DMV triangle can be helpful here when you're doing these problems. But you do need to know all three equations, and obviously you need to be able to use them to do problems. We're going to do our first example here. We'll start out pretty easy and then we'll work into some more fun examples. So this problem says you have a piece of wood with a mass of 11.2 grams and a volume of 23 milliliters. It wants to know what is the density. So we're solving for density here. So the hardest part about these density problems is making sure you pick the right equation. So whatever you're solving for, in this case density, you want to use that as the equals. So we're going to use the D equals because we're looking for density here. So we have to use the density equals mass divided by volume equation because we're trying to solve for density, right? And then we can just plug in here. They gave us a mass of 11.2 grams. So obviously your mass in the problem doesn't have to be written first. It's going to be the one that has your units of mass with it, in this case grams, all over the volume, which is 23 milliliters. So this would have to have units of volume associated with it. Notice these units would not cancel. Grams divided by milliliters don't cancel out. All right. So when you plug and chug this, you do have to pay attention to sig figs. So it's a division problem here. Density problems are either going to be multiplication or division. So you're going to go back to your original problem, count sig figs, and use the least. So this term would have two sig figs. This one would have 3. So your answer can only have 2 sig figs in it. So when you plug and chug this and round to correct sig figs, it should be 0.49. And then your units, which don't cancel, are going to be grams per milliliter. All right, so get used to having those units for density. And it could be grams per centimeter cubed or something like that, but it's usually going to be your mass divided by your volume unit. Follow your sig figs, show all your work, and then obviously pick the right equation here. So this was a pretty simple example to start this out. Another example to try here, we have mercury metal. It's poured into a graduated cylinder that holds 22.5 milliliters. The mercury used to fill the cylinder weighs 0.3060 kilograms, and we want to calculate the density in grams per centimeter cubed of mercury. So in this problem, what are we solving for? We're going to find density. It says calculate the density. So we have to use the D equals equation because we're solving for density. So we're going to have to use D equals mass over volume here. All right. So a couple of things to point out with these density problems. Obviously, you need to pick the right equation, but then you need to watch your units. Density problems become like a conversion fest here. You have to pay attention to your units. So if you didn't learn dimensional analysis and learn those conversion factors, that makes density a little problematic here. So if you notice, I need mass divided by volume. When I look at the problem, they gave me the mass in kilograms, but the problem wants me to find the density in grams per centimeter cubed. So I can't plug that kilograms in. It wouldn't give me the right units. So you're gonna have to convert them first. So you always need to watch your units in these density problems. So you might be doing a dimensional analysis problem here within your problem, and you have to show all your work. So I have 0.3060 kilograms. I got to get this to grams. So I put my multiplication symbol, I put my conversion line, whatever unit's on top immediately goes on the bottom, so kilograms. And then we say, okay, do I know a conversion from kilograms to grams? Well, yeah, we know that there's 1 kilogram for every 1,000 grams. Kilograms on top and bottom, they cancel. So your units now are grams, which is what we want. When we plug and chug this, it comes out to be 306 grams. Now, somebody might say, well, that's not the correct sig figs here. Well, obviously, with correct sig figs, this would be 306.0 grams. But by not having that zero there, it doesn't change the number in any way. It's not going to change my overall end answer by not having a zero. The key is you need to realize you need to use the numbers from your original problem to determine your sig figs. So just be careful with that. Realize that you dropped off a zero here because it didn't matter. Use the numbers from your original problem to determine sig figs. So now we can plug the mass in. We have 306 grams all over the volume. They gave me the volume in milliliters. We want the density in grams per centimeters cubed. This is where I wouldn't need to see this conversion. It's a 1-to-1, if you remember. For every 1 milliliter, there's 1 centimeter cubed. At this point, I don't need to see you do that simple conversion. Obviously, you do need to show your conversions for other things, but the 1-to-1 I don't need to see. So this is essentially 22.5 centimeters cubed on the bottom because of the 1-to-1 conversion. All right, so when I plug and chug this, all right, you do have to use correct sig figs. You're dividing here, so you count sig figs and use the least. When you look at your two numbers in the original numbers here in the problem, your least amount of sig figs is 3. So your answer has to have 3 sig figs. So when you do your math, it should come out to be 13.6 grams per centimeter cubed. Remember, the grams in the centimeter cubed would not cancel. So this is the minimum amount of work I would need to see for this problem. Show your conversions. Obviously, watch your sig figs, show your units in your answer as well. This example is a little bit more fun. We have a piece of wood with a density of 0.82 grams per milliliter and a volume of 0.031 liters. We want to know the mass of the wood in milligrams. Okay, so pay attention to that. Sometimes these problems tell you specific units you must be in, but according to this problem, we are solving for mass. So we have to use the M equals equation. So you need to know that it's M equals density times volume. Make sure you know these equations here. All right, so I'm ready to plug in. They gave me the density in the problem. It's 0.82 grams per milliliter. But if you notice, the volume here is in liters. The density is in grams per milliliters. The milliliters and the liters would not cancel if you tried to plug this in. You got to have your units matching up here. So you would either have to convert your grams per grams per milliliter to grams per liter, or you would have to convert the liters to milliliters, which is what I'm going to opt to do because it's a little bit easier. So you have to show your work here. You have 0.031 liters, multiplication symbol conversion line. Whatever units on top goes on the bottom, so liters. We know that there's 1,000 milliliters for every liter. Liters on top and bottom cancel. So when you plug and chug this, it does come out to be 31 milliliters. All right, so now you can plug that in for your volume and your milliliter units would cancel. Think about this. You're solving for math. Your problem is going to spit out units of mass, which would be grams. But the only way that happens is if your volume units cancel. Okay, so some people need to think about it. Essentially, what you're doing here is you're taking grams per milliliter and you're timesing it by a milliliter. So essentially, that makes the milliliter on the top and the bottom, so they cancel. Your end units are grams. You don't have to show that part, but I want you to realize you are spitting out grams here because your volume units cancel. Okay, so when I solve this, all right, I get 25.42 grams. I didn't sig fig this yet because, pay attention to this, the problem wants this mass in milligrams. So you can't miss that. So I have my 25.42 grams, and I have to do another conversion here. So obviously, grams are on the top, so they immediately go on the bottom. I know there's 1,000 milligrams for every 1 gram. So you still need to know those conversions. Those conversions are very important here. Grams on top and bottom, they cancel. So now when I plug and chug with correct sig figs, it's come out to be 25,000 milligrams. That would be the correct answer. Make sure you circle it or box it. Your sig figs and your units need to be correct as well. So you need to make sure you're showing all your work in these problems. So our last example here has us looking at aluminum. It says aluminum has a density of 2.70 grams per centimeters cubed. It says what is the mass in kilograms, so be careful of that, of a cube with a side of 6.78 centimeters. All right, so according to this problem, we're solving for the mass. So we have to use the M equals equation. So you need to know mass equals density times volume. So we plug in. We have the density of 2.70 grams per centimeters cubed. Remember, you do need to watch your units here. When I go to plug in volume, though, this is where I have a problem. They didn't give me a volume. You need to realize that they told you the side length of a cube to be 6.78 centimeters. That's a unit of distance. That's not volume here. All right. So you have to realize, oh yeah, to figure out the volume here, you have to do length times width times height. All right, keep that in mind. Volume is length times width times height if you're given a distance unit. In this case, it's a cube. So essentially, it would just be the side length cubed. So 6.78 centimeters cubed. Remember here, it's not 6.78 times 3. It's 6.78 times 6.78 times 6.78. Be careful with that. People mess that up all the time. When I do the math here, it comes out to be a pretty big number. It comes out to be 311.665752 centimeters cubed now. Because remember, you did centimeter times centimeter times centimeter, which is centimeters cubed. Centimeters cubed is a volume unit. So don't, cut off any of your number. Use the entire number here that you got in your problem so that it doesn't mess up your final answer in sig figs. So that's the volume here that you need to use. So anytime you have a cube where you need to do length times width times height, if you have a kind of unit of measurement here, distance, you have to make sure you're doing that, and then you should have a cubed unit as your volume. Notice the centimeters cubed here would cancel when you did the math, which is what you want because you want to get a mass here and your unit would be grams. If those centimeters cubed didn't match up, they wouldn't cancel out. So you gotta watch your units in these problems. Make sure that they line up and that they cancel out. So when you do the math here, this does come out to be 841.4975.304, but your units are grams. Pay attention to your density here. That was in grams, so your units are going to be grams here when this spits out the mass. The problem wants kilograms. So you have to do another conversion, multiplication symbol conversion line, grams on the bottom. We know there's 1,000 grams for every 1 kilogram. Grams cancel. All right, and now you're going to be ready to sig fig. Go back to your original problem, count sig figs, and use the least because we were multiplying and dividing here. So it's going to be 3. So when I do this, it should be 0.841 kilograms with correct sig figs and units. So just be careful with these density problems. Choose the right equation. You need to know all 3 equations, and then watch your units. They do usually involve a lot of conversions in these density problems. The last part of these density notes are going to focus on some of the concepts involved here with density, which are just as important as the math. So you do need to know the density of liquid water at room temperature. At room temperature, the density of water is 1 gram per milliliter, or 1 gram per centimeter cubed. That's the only substance that you're required to know the density of. And it's pretty easy. It's just 1 gram per milliliter. What's interesting here is when water becomes ice, its density actually decreases, which is kind of unique here. It actually drops to about 0.92 grams per centimeter cubed. And it's all due to the fact that when it forms this solid, when it lines up perfectly and forms the solid, you get some air trapped in there. So it actually reduces the density. So if you think about this, what's really neat is if you put an ice cube in a glass of water, the entire ice cube doesn't sit on top of the water. Part of it is above and part of it is below the water. So about 92% of ice is below the water, and then the other 8% would be above the water. So if you look at this, the next time you put a piece of ice in water, you will actually see that only about 8% of it is above water. This is actually very kind of important here because of something like the Titanic. If ice sat entirely on the water, the chance of them seeing that iceberg would have been, much sooner, and they would have had been able to turn probably better because they would have seen it. But because most of it was below the water, they didn't see it till later. And then not to mention that part that was below the water is what poked holes in the ship. All right, so you definitely need to know the density of water here. So how does something actually float? Anything that's lower density would float on or in a higher dense item. So we just said that ice is less dense than water. Water is 1 gram per milliliter. Ice is 0.92 gram per milliliter. So less dense things float. So you definitely need to know that. Most wood floats because most wood is less dense than water. But it doesn't have to be just a solid with a liquid here. You can think about this in terms of gases. Helium is less dense than air. That's why when you fill up a balloon with helium, it goes and rises up. Okay, so anything that's less dense would float. A ship is less dense than water. That's why it floats. So this might be a little mind-boggling here because if you think about it, a ship typically going to be made of steel. If I took a piece of steel and threw it in the water, it's just going to sink. But a ship with everything on it, you put that in the water, it's made of steel, but it doesn't sink, okay? Because the ship has a certain amount of air on it, okay, which is going to keep it buoyant and keep it being less dense here than the water. So you do need a certain amount of air on a ship. If you were to get too much water in some of your tanks that need to be empty, you would start to sit lower in the water, and there's a greater chance that a wave could topple a ship. So you do have to have certain compartments on a ship to be air in order to keep the ship less dense than water. So anything that's less dense would float. This table is just showing you some common densities of different substances. You can look it over. Remember, the only one you're required to know is water, which is 1 gram per milliliter. All these are just for your reference. You can see something like gold is pretty dense. It's 19.3 grams per centimeter cube here. You can see air is 1.2, and if you compare that to helium, all right, it's only 0.166. So helium is definitely less dense than air. That's why it floats. When we do our hydrogen balloon and we fill it up in the balloon, it would be even less dense than helium, so it really floats. So again, these are just for your reference here. There is a relationship between density and temperature. Typically, if the temperature goes up, the density is going to go down. So it's an inverse relationship. If one goes up, the other goes down. So obviously, then if the temperature drops, the density is going to go up for a substance. Water does not follow this. Okay, water is kind of the weirdo, but typically all the other substances we look at, they're going to follow this inverse relationship. If one goes up, the other goes down. And yes, a lava lamp shows this relationship perfectly. So I'm going to walk you through this relationship and show you how this actually applies to a lava lamp. So what most people don't realize is there is a light at the base here of the lava lamp. It's one of those old incandescent light bulbs, which gives off a lot of heat. All right, it's an old school style of light bulb. About 90% of the energy you put in to the light bulb is given off as heat. So it's very wasteful. The newer light bulbs we have now, like the CFL or LED, are much more energy efficient, but these light bulbs give off a lot of heat. So that's why we use them in lava lamps or like easy bake ovens. All right, so they're always kind of hidden below there. There's usually like a metal coil at the bottom that just helps transfer heat here. So when you turn your lava lamp on, that heat from the light gets transferred to the coil and it starts warming up that lava. So we're increasing the temperature here of the lava. And people always say, well, what is the lava? It can be a bunch of different chemicals. It depends on the maker here. Sometimes the chemicals in there are proprietary information, so they don't really release what those chemicals are. But the key here is by turning on that light, you're starting to warm it up and increase the temperature. As we increase the temperature of the lava, all right, what's going to happen here is you increase the temperature, the density is going to start to drop. So it's this inverse relationship here. So whenever the density goes below the density of the liquid, a piece of the lava will break off and start to float up. All right, so let's just say the liquid in there is water. Again, it doesn't have to be, it could be some other substances, but it just makes it a little bit easier here. So density of water would be 1. As you increase the temperature, the density of the lava drops. When it gets below 1, it's now less dense than the liquid, and less dense things float. So a piece of it breaks off and starts to float up. Eventually, you get a piece or 2 or 3 at the top, and as they're sitting at the top, they are away from the light, so they start to cool. So the temperature is dropping back down. So the temperature is dropping. You can think about what would happen here to the density. It's inverse. So the density is going to start to go back up as it sits at the top and starts to cool. Eventually, you get to a point here where the temperature has cooled enough that the density has gone up above the density of the liquid or above the density of the water. So now it's going to be greater than 1. All right, so it's going to sink back down because less dense things float. All right, so as you drop the temperature, you're going to increase the density, making it more dense than the liquid. So it's going to float back down. This inverse relationship here with the density and the temperature. And then lastly, the lava piece would rejoin the coil here, start to increase the temperature again, and the whole process would continue. When you increase the temperature enough and you decrease the density below the density of the liquid, less dense things float, and the lava would just float up, and the process would continue. The important part to remember here is the lava lamp works because of chemistry. This relationship between density and temperature makes this work. So chemistry is not all bad.